And there we got everybody now. Okay, so we're talking again about black body radiation, and I'm going to cut right to the worksheet because today's activity, I guess, is that we're going to do some calculus, and we're going to divide up into two groups, I guess. 1, 2, 3, 4, 5, 6, 7. Missing Sam and somebody else. Anyway, we'll divide up into two groups, and you're each going to do a problem. And so let me share the problems with you. And iPhone, AirPlay, come on. Screen mirroring, yes. Boom, put that away. All right, and so I guess the first thing I want to say is my fonts for making these worksheets up. There's my little thing. Sometimes not the greatest. Just so there's no confusion, when I drew this up on the worksheet, it was more of a script I. That's what that thing is. This is Planck's distribution, okay? And a couple of things about it, I guess. You've got a bunch of constants, and it's a function of both wavelength and temperature, okay? And what we want to get out of that is Wien's displacement law, which is this guy right here. And if you remember what this curve looks like, if you plot versus wavelength, what this power spectral density is what I called it. I've heard people refer to it as the spectral density. It is the number of watts per meter squared per usually nanometer of wavelength. And the curve looks something like that. And what we're looking for, because what Wien came up with a law to explain, is that peak. And so if you want to find that peak, I guess the answer can be gotten if you take the derivative of that function with respect to wavelength and you set it equal to 0, well, you'll get the right answer. And you should be able to recover Wien's displacement law from that. Okay, now if you look at it, it's a fairly tedious derivative to do. I do have one piece of advice, actually a couple pieces of advice. The first thing I see is that if you look up in the exponent right here, well, you could write that over and over and over again if you want. My advice is call that X, okay? And at some point, you have to take your derivative first, but then quickly substitute it away. Another piece of advice I have, I'm going to stop sharing this with you and show you another tool that I think is valuable when doing exercises like this. Share screen, and let's see, where do I have it? I have Google Chrome. Sorry, we got to get over to another. Yeah, Wolfram Alpha. Hopefully you're seeing that. Yep, I see the green border. Wolfram Alpha is a powerful tool, I think, to help you do math. And what I did is I just searched for it. Wolfram Alpha it will come right up. And I've got it set up. It'll do all kinds of calculus problems for you. I'm going to show you a definite integral first. And so you can see if you want to integrate this function from x, for x over, so that's saying dx basically, from 0 to infinity, hit compute. What I recommend you always do is make sure that whatever integral you put right here is the integrand, it shows up right here, and then it gives you the right answer. And so, there's all kinds of integrals you can do over and over and over again. It takes all the tediousness of doing integrals completely out of the problem. Okay, so that's one. It'll also do derivatives. I don't know if it has as cool a template. I forget derivative. I can't spell today. Derivatives. And so you put the function you want to take the derivative of. In this case, I just think it assumes x. And remember, you're taking the derivative with respect to lambda in our problem. but this is kind of an important step, is to be able to take a derivative and set it equal to 0 and find the maximum. Stop sharing this, go back to my AirPlay, my Notability. Where'd my pen go? There it is. Share that. Just a 3-ring circus here. All right, we're back. Put that away. And a couple of problems are going to creep up when you try to take this derivative. The first thing I want to tell this group is, let's say you take a derivative and you have something like 3x, and this isn't what you're going to get, plus 5 over 7x plus 2 is equal to 0. The thing you ought to realize, once, if whatever this function is that you take a derivative yields you something like that, in order to be 0, that always means the numerator has to be 0. And so in this case, that would tell you that x was equal to minus 5 over 3, right? So remember that when you're doing these, I guess it's either a maximum or a minimum is what you're trying to find on the curve. The turning point problem in calculus, once you find the derivative and you set it equal to 0, there's a lot of terms that don't matter. The bottom line is, if you have a ratio, the numerator is 0, makes the result 0. And in this particular problem, you're going to find an equation, and I'll just tell you what the interim steps should be. You're going to find that 5 is equal to x e to the x over, of all things, e to the x minus 1. And of course, x here is that substitution that I recommend you make. I always try to do that. Okay, so when I say x, I mean that thing. Anybody know how to solve an equation like that? Because that is actually what your result will be if you do the derivative correctly. You'll get from that to that result. It'll take a couple steps of algebra, no doubt. Anybody know how to solve that?
Take log on both sides.
Okay, so you do that, right? 5 times e to the x minus 1 is equal to x e to the x. And so you got 5 e to the x minus 5 is equal to x e to the x.
Do you divide by e to the x?
Yeah, I'm not sure that's going to get you to a right answer, though, because of that multiplication. Okay. I think this is something called it's an equation that can only be solved by numerical iteration. All right. Yeah, see, this term right here is different from that term. You divide by e to the x, which some of you suggest here. Okay, so that would be 5 minus 5 over e to the x is equal to x. And you still haven't simplified the equation to a point where I have any algebra tools that I've ever learned that allow you to solve it. And so, the answer, I guess, is you have to try to iterate. And so you go, all right, well, let's let, I don't know, start with x equal to 1, see what you get. All right, and let x equal to 2 and evaluate both sides, and x equal to 3, and you iterate through. The good news is, in the day of computers, a program like Wolfram Alpha that I just showed you, if you type in this equation, it will give you the right value for x. It'll do that numeric approximation for you, and you don't have to do that. Back in my day, literally, that's what we do. We'd write a little computer program. Okay, let x equal to 1, evaluate the right-hand side and the left-hand side, see if they're equal. Nope, they're not. Try x equal to 2. Did you get any closer? Did you get any further away? Evaluate both sides of the equal sign. Do it for x equal to 3, x equal to 4, x equal to 5. Keep going until you figured it out. And if you realize you were not close when you started with x equal to 1, maybe jump to x equal to 10 or whatever it is. But you had to guess at an answer, see if it worked, and then try to iterate down until you got the right answer. The good news for you all, you don't have to do that. Okay, the computer on a program like Wolfram Alpha, Mathematica, I think even Python will do stuff like that for you, solve numerical problems. So just use a program. MathNet is out there. All these things are available to you. In any event, once you solve that, you should get an equation. Of course, since I said X will have both lambda and T. If you put all your constants in the right place, you should be able to recover the Wien's displacement right out of Planck's distribution for the power spectral density. Okay, so half the group, that's what you're going to do, and you'll come back and show us how that went later on. Now, the second problem that half of you will do, we'll start with the same thing, and again, script I right there, the power spectral density. And what we said is, and I didn't give it a symbol, I don't know if I gave it a symbol on Monday, but people often use R, because remember, this is watts per meter squared, and then and I'm going to say most people in our class are going to use nanometers right there. And if you integrate over all the wavelengths, what you'll get is the intensity, and that'll just be watts per meter squared. And so you might call it I. Some people like, our textbook uses a symbol R for that. And of course, you multiply that by an area on Monday in order to get the total power. And that was the calculations we did on Monday. And so what you guys are gonna have to do, this group, you're gonna have to do this integral right here. You're gonna have to plug that thing right there. And you can see you're integrating over wavelengths. So wavelength appears right there, and it also appears right there. So it's a tedious integral. I do recommend some kind of substitution. I think if you try to just put the integral into Wolfram alpha, even if you use definite integral the definite integral, which gets you and I'm going to switch over in just a second, integral, boy, I can't spell. Oh, temporarily unavailable. So I'm not going to show it to you anyway. Hopefully it'll come back here in a minute. If you just try to put that integral into Wolfram alpha, I think it's going to be too complex. Now, a couple things you can do. You can lump your constants all together, call them like A. So that 2 pi c squared Planck's constant, don't put that into Wolfram alpha. It'll choke if it tries to do that. And of course, your limits, what are your limits on this integral? Well, your limits are, where this is our curve, we're finding the area from 0 all the way out, that thing asymptotically approaches all the way out to infinity. So that's the limits on the integral which you're doing. Okay, and when you're done, remember, you should be able to get the fact that this is no emissivity, because we dropped that. We'll assume it's 1. You should be able to show the Stefan-Boltzmann law that your result of your integral is proportional to the 4th power of temperature, and all the constants that are out front should give you Stefan-Boltzmann's constants. Okay, and so that's the task for the other group. Now, a little bit mathematical, so you're going to work together. You can divide up your labor. I did, so you don't have to look up, I did give both groups the constant. The first one is K in Planck's distribution. The second is, of course, Planck's constant. Both tedious numbers. I would not put them in until the very end once you're ready to verify your two constants, the Stefan-Boltzmann constant and, of course, the Wien's displacement law constant. All right, any questions what we're doing today? So you're going to be off doing that. I'll create groups here, stop sharing this, and we'll go into groups, breakout rooms, 2 groups, and here's how it'll go. So Amaya, Inaya, Max, and Shneha, you're doing problem 1. You're taking the derivative and getting Wien's displacement law. Justin, Prince, and Zayed, you're doing problem 2. You're doing the integral, and you're going to try to recover the Stefan-Boltzmann law. Questions on that? All right, you got plenty of time. It's only quarter of. I'm going to call everybody back probably around 5:10 after, and so we can go over it in about the last 10 minutes of class and make sure we see how you do these problems. All right, have fun. Five, 6, 7. Missing Sam. Eh,
Okay. So first, what I would say is we're gonna do the product rule and the quotient rule.
you know, can I make an advice? I
Yes.
hate the quotient rule. If you like the quotient rule, knock yourself out.
Is there an alternative?
How about you take the lambda and you write lambda to the -5 and bring it up to the numerator, right? You got all those constants, so just call them C, right? And then, yeah, lambda to the -5. And then the other one you got is you got the quantity of e to the lambda, I'm sorry, HC over lambda KT. And -1, put that in parentheses and raise that to the -1 power. Good. And now you got a product rule, right? First times the derivative second, second times the derivative the first. That's my recommendation.
Nice.
And
Thank
that, because I do it that way, I only have to memorize one rule. I always hate that you square the thing, then it's first
The
time.
low, then the high, minus the high and the low.
Yeah. This is easier, I think, for me anyway. Yeah, and don't forget the chain rule too, unfortunately. All right, you guys are off. Have fun. It's a fun math problem.
Is it though? Is it?
Yeah, bring down that -1.
Yeah, so into -1 multiplied by, again,
And we still have our constants in front of all this.
Yeah, you can put those in later if you want.
Yeah.
You can
so we
put
just
them
have
in
to
later.
remember it. Yeah.
In fact, if you think about it, if you're going to set this derivative equal to 0, those
It's not going to even
yeah,
matter.
they're going to
then.
cancel, right? So you don't even have to write them. You guys are off though. Have fun.
So it's just
Thanks.
here is
So that we,
like instead of writing HC over that big constant, like we just use X.
yeah, it makes it, but we're still substituting it out because then we would kind of define X would equal something, right? Like HC or something.
Yeah. Yeah, here's what I would tell you. If I could just interrupt. Let me see. I'm going to put a pen in because you guys did something that is one of my pet peeves on integrals. Okay, so let me find my pen to annotate here. Few options.
Oh, did I not do this?
Yeah, that's my pet peeve. Okay. And now,
There you go.
Exactly. And now what I would recommend for this X, HC over lambda KT is equal to X.
I see.
Yeah.
Okay. Where is it? Lambda KT. Because all of these are, what about T though? Aren't we integrating?
You're integrating over lambda.
Oh yeah, you're right. Okay.
Yeah, so what I would do is in this now solve for lambda.
Okay.
Which you just wrote right there that, yeah, solve for lambda now.
Okay, lambda is gonna.
Yep. Okay, now you need d lambda, so you got to take the differential of that. That's kind of a pain.
Wait, what do you mean? Why do we take the differential then?
Because you need, this is my pet peeve of substitution. It's the reason you need to substitute right here. And so you need d lambda. Of course, that's going right there. And then this right here will replace all of this stuff.
I get exactly what you're saying. This is basic substitution. Oh yeah.
Exactly. And the last thing, don't forget to substitute away your limits too.
Oh, yeah, let's use
And
substitution.
so when when lambda is 0, that means X is infinity. And when lambda is infinity, that means X is 0. All right. There was a question. Somebody? Everybody good? All right. So d lambda, I'll help you out here because I enjoy calculus. I do. So let's see. It's going to be all those constants. HC over KT. And that's really X to the -1, right? So you bring down that negative sign and it becomes X to the -2, doesn't it?
Yes.
How did I do there?
Yep.
And then with a dx. Yeah, with a dx. I'm sorry, not a dx. Yeah, with a dx. Yeah. Now, did I do something wrong there? Something doesn't look right. Something doesn't look right. dx. It's definitely lambda.
I can't spot it. No, I think. What do you guys think? I don't.
I think it's right because I think when the minus and then x minus 2 unless
How did I do that though? C over
because
K.
I think
Lambda.
did you take x as a variable and then we differentiated it?
Yeah, I went a different path and I'm getting a different, and I should get the same answer on this one. So d lambda is dx. Yeah, I can live with what I did there. Okay, go ahead. Yeah, there's nothing wrong there. It's just a matter of which way you want to go for it.
Perfect. No, that's.
Yeah, I think you'll be okay. And substitute that in. Yeah.
All right, I'll just.
All right.
Thank you.
You
Perfect.
bet. Yeah. I'll leave you guys.
Yep. All right. Perfect. All right. So
And that's times. And then I got d lambda, which is hc over kt times x minus 2.
And is it negative?
The negatives cancel out.
Oh, yeah, they do.
And all that is multiplied by
Yeah.
lambda to the negative fifth.
Yes.
Okay.
We do lambda kt over hc
Yes.
as x.
Yes. Yes. All right. I think it's time now to stop writing HC over lambda KT. Call that
I'm
X.
so done with that. Yeah.
Yeah, I
Let's
think,
just call it X.
yeah, call that X. Because the lambda is going to cancel away for you, right? I think. Yeah, because you got lambda to minus fifth in the one term and lambda to minus six in the other. There you go. Good. Good. Yep. Yep.
Okay.
Yeah, looking good. Now, a couple things. My next piece of advice, I said, consider multiplying by lambda to the sixth e to the x minus one, because that'll make a lot of that go away, won't it? Yeah, in fact, if you look right here, just a couple things. Come on, I should be able to annotate here. There it is. That and that are the same as that, right?
Yeah.
So you could factor that out. And then
We
you've
can
got,
actually just like cancel
then you
it
got
out
one-
because when we equate it to 0, we know that lambda is not going to be infinity anyways.
yeah, I think that's probably a reasonable step. So that's going to go away. And you can even get rid of one of those two things as well, because you got one that's to the minus two power and one that's to the minus one power. And so those will simplify away as well. And so you're getting close. You're almost there. Keep going. Nope, everything's good. It's darn good thing this is a negative sign, right? Because if that wasn't a
Yeah.
negative sign right there, there's no way those would be able to be equal to zero, and they have to be. All right. All right. You guys are going good. Keep going.
Lambda 5 is a constant. Why did I use, why did I put it in the integral? Shouldn't it be here? Like, that makes more sense. Now we have only x's to deal with.
Yeah,
Yeah. You brought it outside the integral. You can't.
I just brought it out. I was like confused. I was like,
Yeah.
how can we do it or not?
Nope, you can't. Because remember, lambda is a function of x, and you're integrating over x, right?
It makes sense.
Yeah. So you got to put it back inside the integral, and I would use yeah. But remember, lambda to the fifth here. Go back up to what you got for lambda. Some of it you could bring out. Yeah, you got that x right there, right? That's the problem. You got that, but that's all right. So you're going to go lambda to the fifth. That's all of this to the fifth. That can come outside the integral. You got this to the fifth. That can come outside the integral. And that's to the fifth as well.
And only keep x.
Yeah, so some of it's going to cancel. You're going to get, I think you'll have x to the third in the numerator. And I'll get rid of my stuff because it didn't help it necessarily.
All right, so imagine all of this is to the fifth. And okay, this is going to be very crazy. Write it in negative fifth, or should I?
Yeah, you can do that with the -5.
Yeah.
I don't like having negatives too much. Okay.
It's going to go right in here though, right?
Wait a second though. No, I can get it out. Okay, let's write a new equation. Okay.
Well, okay. I see what you. Why don't you just flip your limits around, go from 0 to infinity, and get rid of that negative sign? Is that what you were suggesting?
Not what I was thinking. No.
But you could do it, right? To get rid of that negative sign,
Okay.
just go from 0 to infinity. Flip the limits around, and that'll work.
Oh, you're talking about this negative.
Yeah. Exactly.
Oh, no, I was talking about when you have, x to the power of, whatever, negative, whatever. I was trying to think of that.
Okay. Now I'd
Yeah.
leave it the way it is.
But no, like, yeah, this negative is fine. It's not too big a deal.
Okay.
Yeah. So assuming all of this is correct until now, we'll write this down. And just for simplicity's sake, I will. Wait, do you mean I can just take out? I'm just a little bit low on short algebra over here, so I can just take all of these out completely out of the integral. So it would be like
the parts you can take out are right here. You got the reciprocal of that though, because it's in the denominator. So that's down here. And then the K, this is KT right there, right?
Exactly what you're saying.
It's in the denominator, so you got to flip it.
Oh, okay.
Yeah.
Never mind.
I'll get rid of my stuff. Yeah, there you go.
Perfect. And, oh, sorry. Never mind.
If,
and some of these will cancel.
yeah, some will cancel some of that over there. Exactly.
So,
all right, you guys are rolling. I'm going to leave you alone.
All right, thank you.
You bet.
Okay, just like, okay.
And equals multiplied by KT HC 0.966 KT.
Yeah. And this way it looks different than the textbook. So
You're okay now, because all you got to do now is all those constants better be that constant you're looking for. Better be 2.899 times 10 to the minus third, right? Yeah.
Over.
So that's where that constant comes
T.
from.
Yep, that's where that constant comes from. It comes from H, the Planck's constant, the speed of light. How'd you do this, by the way? I'm just kind of curious.
Which part?
How'd you get the 4.966? Did you go to Wolfram Alpha or something?
Yeah, literally computer.
Yeah, you just did on a computer. That's exactly what I did too. So there you go. And the only thing that might check is take H, take the speed of light, divide it by 4.966, and sure enough, make sure you get that constant, 2.899 times 10 to the minus third. All right. Other groups still working, so you got just a second or two to smooth that up, and I'll go see how they're doing.
Cool.
But you got it. Let me write this down. E, A, S, and M. All right.
We just need to like integrate.
I just need to get some rules in, and then we should be good.
Yeah. Now, here's what I would have done in my day. That integral you've got, I would have gone to an integral table because it is the right integral. Yep. exactly. If I tell you the integral, the answer to that integral, would that be helpful? You can see right away, though, you got what you needed, didn't you?
Yep.
Because you've got that t to the fourth.
Mm-hmm.
That's the big deal, right? And then this guy right here, that's just going to be some constant, okay, and whatever it is when you just go to an integral table. I'll tell you what I did. I went to Wolfram alpha, and let me make sure I'm giving you the right number. I got for that integral, and it's something you can look up, pi to the fourth over 15. All right, so let's make sure I got these here. That's 2 pi k to the fourth. Yep, your constants are all right. And I'll just tell you, if you went to an integral table or to a program like Wolfram Alpha or Mathematica, you'd find that. And so all of these things right here, that has to be the Stefan Boltzmann constant sigma, right?
Wow, yeah, it should be. Yeah.
You can plug it in and prove it. And you know, I think it's worth taking a second just to do it. And I gave you the constant K, the Boltzmann constant. I gave you Planck's constant. Your calculator may choke a little bit because remember this guy right here is something like 10 to the minus 34th. And then you're going to cube that, right? So that's something like, yeah, you can see that a calculator may not like that. 10 to the minus, it's like minus 100 or something, right? 100, let's see, 90, 102, I guess. Some calculators will fail on that, but the answer is your sigma. I think you got the idea though, so we're good to go. Everybody see what I would have done with this integral?
So we can just look it up.
Yeah, you look it up is the bottom line.
We're past the days of doing it by hand, honestly.
Yeah, I don't know. Truthfully, I'm not a good enough mathematician to know how to do that integral, but I think we're good to go. All right, so you guys ready to explain what you did to the other group?
Pretty much, I'm going to just write down the last steps and
yeah, those last couple steps, and I'll erase so that your stuff isn't messed up with my my work. But yeah, the value of the integral is pi to the fourth over 15 was the answer to that integral. And I want to clear. I want to erase because I'm worried about clearing all of your stuff. All right. You did it, though. I'm out of here. We're going to leave.
perfect.
Admit it. That was fun, wasn't it?
Nope.
An honest person. There you go. There you go. We'll let the other group. They were just finishing up their integral, but they've essentially got the right answer too. So both groups were successful today, and they'll explain to you what they had to do because theirs wasn't a whole lot of fun either. And they should be back in just a second. Everybody's back. All right. I guess let me put this away here. And so group one, who was writing? Was that you writing, Max?
Yep.
Want to share your screen with everybody and show them what you did?
Sure. You have to let me though.
Oh, yeah, that's right. Thank you. I got to give you permission, don't I? Yep, there you go. You should be good now.
So this is what we did.
Just, you might want to walk them through just a little bit of the, yeah, that's the key point right there, right where your cursor was. Talk about what you did right there.
Well, first, we
Uh,
didn't want to do the quotient rule, so that's really important. That kind of set the tone of where we were going.
Now, if
That's
you
why
like
it
the
looks
quotient
different.
rule, don't let me bias you, but I just think this way was easier. So I kind of pushed you this way.
So yeah, that's why we have negative exponents on the top, because this way we could only do the product rule rather than quotient and then product rule. And you just have to keep in mind the chain rule. And then after we finish that next line with the chain rule and product rule, then we made that jumble of a bunch of constants, we made it just x. And then we took out what was the same in all the terms, which was x to the negative 6, and then e to the x minus 1 to the negative 1. And then that's when we could set it equal to 0. And then we crossed out those things on the left because it's equal to 0. And then we got that thing on the bottom, which was when we put it into the we put into Wolfram Alpha to find the thingy, the x equals something. And then we made x back into the constant so we could remember what we're even doing. And then we solved for lambda, so it could be Wien's law.
Okay.
That's it.
And if you check it, if you put in Planck's constant, speed of light, and the answer they got for this weird equation that I said you were going to get, 4.966, you should get the value 2.899 times 10 to the minus third. Anybody put in a calculator just to see if I was lying to you? You trust me. You shouldn't. I'm over. Somebody in the 60s said, don't ever trust anybody over 30 because we'll lie to you. And I'm well over 30. So be careful about trusting me, but you will get those numbers. I think you can believe it. Right. Any questions from the other group about how they did it? It was just a tedious derivative. They had a tedious derivative. The second group, you had a tedious interval, right? But it's something you can do. You've got the calculus skills to do it. And then they needed Wolfram Alpha to help them when they got to this weird equation down here by setting that derivative equal to 0. And was it any trouble to find it? Who actually plugged it into Wolfram Alpha?
Me and Sneha. It was really simple.
You literally just type it in and push enter, and it says, okay, x is approximately this, right? So that's a good skill to have. All right, second group, you're up.
Yeah, sharing now.
Okay.
And interesting enough, that x that the first group used, the second group, you're going to use that same x. They did exactly the same x. So.
All right, so somebody wants to go over it?
Sure. So as Professor pointed out, we wanted to use X so that things could be a bit simpler now. So we, just as you said, we took the E power thing and put that as X. So we solved for lambda, and so what lambda was, we got what dy was, and then we kind of just removed all the constants outside, and we're left with the expression 1 over the expression right there. And then for the bounds, we also we flipped our bounds by substituting the original one to find what they are for X. And then, yeah, kind of just solved it.
Yeah, so yeah, pretty much after that, it was basically doing a little bit of algebra and stuff, substituting, the lambda we had over here up to this, and kind of solving, making it equal to x, where we were able to get this and get all of this stuff out, which got, we had a little bit of, canceling, and it was simplified to this at the end, which, yeah, plugging into calculator should give us this.
Yeah, and obviously, he said just a little bit of constants. It's really easy to make a mistake right there where he starts canceling things, and keeping track of it did a good job. And so the key, though, is you got t to the fourth, right? Which is what the Stefan Boltzmann law predicts. And so that was good. And then all of those constants, what should they be?
Stefan Boltzmann.
Stefan Boltzmann should be sigma.
Yeah, as as Professor said, honestly, like doing Planck constants and cubing it and timesing it by 15. Honestly, we didn't have the chance to give this a shot.
And I think some of you will find your calculators don't work because remember, it's what we were talking about in the other group. H is something like 6 times 10 to the minus 34th. And if you cube it, it'll be 10 to the minus 102. And your calculator may not let you put in something times 10 to the minus 102. It may be too small a number for some calculators. So the order at which you would do this to get the number of the Stefan Boltzmann constant really does matter, right? And so you might not be able to just cube H all in one fell swoop. And those are things people go, my calculator's failing. And it's just, you got to recognize calculators have limits on what the biggest number and what the smallest number they'll deal with is. But it will come out to be the Stefan Boltzmann constant. Trust me, I wouldn't lie to you guys. All right. Any questions on anything we did today? It's an important piece of physics linking what Max Planck did with what was done before he came around, what Wien did with his displacement law, and what that Stefan and Boltzmann did with their T to the fourth law that we worked with on Monday. When Planck came with his distribution for what a black body spectrum looks like, it had to work. It had to give you the results that both Wien and Stefan and Boltzmann had come to. And of course, you showed today that it does. Okay, so Planck comes after the fact, and his stuff is good too. All right, I think I kept it 2 minutes early. I'll put the grades in Canvas. You don't need to upload anything. I hope you enjoyed the experience of going through those two problems because they're important for physics people to see and see how everything hangs together. Any questions?
I was gonna ask, not really related to this, but in I think 1 week, like next Wednesday, we have a test.
Thank you. You do.
All right, nice.
Yes, you do. Okay, and so it will be open book. It will be a lot like one of these worksheets. I may include 1 or 2 WebAssign problems as well. That's what I'm doing with my 101 students. So yes, a week from today, there won't be class. Instead, you'll find in Canvas an exam, a midterm exam, much like the worksheets we've been working. You'll have to upload it. The rules for it are open book. You can use any of the notes on Canvas, any of the notes you've taken, but you can't talk to anybody and you can't go search in the internet for solutions. And so that specifically rules out something like Chegg as any place to go. And what I'm going to do is I'll load it up in the morning on next Wednesday, and you can work it any time during the day on Wednesday. It'll be due 1 minute before midnight, 23:59. You'll have to get the solutions loaded uploaded into Canvas. Does that answer your question?
Yep.
All right.
Thank you.
Yeah. Thank you for reminding me. I meant to say that at the start and just simply forgot. Other questions? All right. I'll let you know the exact scope of which section. It'll certainly cover up to black body radiation, what we did today. Friday, we're going to talk about photoelectric effect. That'll also be on the exam. And I think Friday's material on photoelectric effect is where we'll cut off the exam for the scope. The material we do on Monday will not be included on the exam. All right. Hey, you guys have a great day. We'll see you on, what is today? Today's Wednesday. So we'll see you on Friday.
Thank you. Have a
Take
good
care
day.
now. Oh, and I'll stay around. Yeah, there you go. Clapping. I'll be around. We'll keep this open if anybody's got any questions.